Hello, everyone. Thank you for listening to my talk, Quantum Cast Iron Cooking. I'm Rob Hackew. Let's get started. This is a cast iron skillet. As the name suggests, it's made by pouring a low carbon content iron alloy into a mold and allowing it to cool. The result is a tough, heavy skillet which can be used in the kitchen, on a grill, or in a campfire. Although they come in many shapes and sizes, they all have one thing in common: a thin layer of scratch-resistant and anti-stick coating, which is dubbed seasoning. This seasoning is created by applying a thin layer of vegetable oil or animal fat to a hot piece of cast iron, which is then kept at over 250 degrees Celsius for around an hour. We use so-called drying oils, oils with long, unsaturated chains of carbons, which can cross-link upon high-temperature decomposition. It's believed, on online forums, that the seasoning process leads to a biopolymer-like coating which adheres to the iron. Each subsequent use of the pan with oil-containing foods will increase the seasoning's thickness and impart more flavor. The seasoning is non-toxic and regenerative, unlike modern Teflon-coated pans, which lose their coatings over time. Moreover, cast iron cleans easy with just a scrub brush and hot water. These reasons and more are why cast iron cookware have been popular for hundreds of years around the world. Although the seasoning is likely formed through cross-linking in the bulk, the interactions between the iron surface and the oil molecule are not well understood. One study conducted in 2020 by Qinjie Gao and colleagues sought to study the interaction between iron woks and beef tallow, which is rendered beef fat. Their studies suggested that beef tallow catalyzed the formation of iron oxide nanoballs, which allow the oil to seep inside the surface. However, the authors didn't look at any particular iron-carbon interactions. The oil simply sits between iron atoms. Additionally, this study suggests that seasoning cannot occur without the presence of oxygen or water. There may be further interactions between iron and the oil which instigate the seasoning process in lieu of other initiators. The seasoning process is initiated by radical carbon formation, normally caused by oxygen or water abstracting a hydrogen. If it was more favorable for iron to abstract a hydrogen over absorbing the molecule, then it may be possible for the iron surface to catalyze the seasoning process by radical formation. I sought to model these systems using Psi-4 in order to determine the energy of various iron-oil interactions. I began by creating some test molecules and optimizing their geometries in Avogadro, a molecular modeling software. Since the total additives in cast iron are less than 5% by mass, they were neglected for a pure iron structure. Iron takes on a body-centered cubic structure, and I wanted to investigate two possible adherence sites, on the top of the cube, which I call iron 5, and along the edge, iron 3. The molecule chosen as a model drying oil is C6H10. It's assumed the interactions between the oil molecule and the iron surface are local, so I only needed to investigate what happened immediately at the site. The states I chose to investigate are the iron and oil by themselves, in the absorbed states, and a potential reaction that begins with the abstraction of a hydrogen, TS1, the movement of a radical to an adjacent carbon, TS2, and finally, bonding between the carbon radical and the iron surface, TS3. After geometry optimization, the single point energy of each molecule was determined using density functional theory at the Perdue-Burke-Erzenhoff 0 or PBE0 level, with an augmented CC-PVDZ basis set. The PBE0 is a hybrid generalized gradient approximation which mixes PBE and Hartree-Fock exchange energy in a 3-to-1 ratio, and it can provide good energy estimations for metals, although it can often overbind. The AUG-CC-PDVZ, or Augmented Correlation Consistent Polarized Valence Double Zeta for long, adds a diffuse function d orbital to heavy atoms and a diffuse p orbital for H atoms. To aid convergence, core iron electrons were frozen and damping was set to 5%. Maximum Overlap Method, MOM, was turned on after 80 out of 100 iterations, which helps greatly with oscillating values. These parameters, along with the optimized geometry of the molecules, were used in the Psi-4 suite of programs to calculate the energy of each state. The results I obtained were quantitatively dubious, but told a qualitative story. For the iron 5 molecule, the quintet state was the most stable starting configuration. This points towards the surface iron molecules each having a free d electron. These electrons are probably what align the oil molecule diagonally over the surface, and is what led to the investigation of the triplet iron 3 molecule. The energy of adsorption is calculated as the energy of the iron surface and oil together minus the energy of the two molecules alone. The calculated adsorption energy for the iron 5 and iron 3 systems were about 217 and 34 positive Hartree, respectively. This indicates a large barrier to adsorption, although much less so for the iron 3 case. Obviously, these numbers are pretty large, but that's why I say the qualitative story is more important than the quantitative one. For the iron 5 surface, there is about a 9 Hartree drop in energy upon hydrogen abstraction, but then an almost 200 Hartree drop upon entering TS2. What's more, there is a 22 Hartree barrier to TS3, indicating that iron 5 prefers to move the carbon radical but not to react with it further. This opens up the possibility of the carbon radical beginning polymerization, which would mean the iron surface could initiate the seasoning process from the bottom up. The iron 3 surface has an equally interesting result. After adsorption, the energy decreases by more and more each step until it settles on TS3, where the carbon radical formed a bond with the open iron atom. It appears that the formation of the iron-carbon bond is enough on its own to pay back the energy of adsorption. In the iron 5 case, on the other hand, the iron prefers to stay in transition state 2, which gives the carbon radical the chance to initiate cross-polymerization. In a future study, the addition of more and larger oil molecules will provide better insight into the possibility of cross-polymerization. There are two main takeaways here. One, if the large energy barrier to adsorption is overcome, then it is energetically favorable for an iron molecule to abstract a hydrogen. This means that contact of the oil with the bare iron surface may be enough to form a carbon radical. More importantly, depending on the absorption site, the carbon radical may either participate in a polymerization reaction or attach to the iron surface. These results indicate that there may be surface carbon interactions in some areas of the chain, while in others there would be polymerizations. This combination of surface bonding and polymerization may provide a more complete reasoning for seasonings tough in a hydrophobic nature. Of course, some of the assumptions made in this study are quite generous, such as a perfectly clean adsorption site. Future work could include site competition, or it could try to simulate the effects of oxygen desorbing from the iron sites into the oil, which could also start the polymerization reaction. For any future study on this system, it would be wise to implement a plane wave basis set, as they are more representative of both the repeating bulk metal and alkene structures. Including the presence of water or oxygen in the oil, both of which can catalyze oil drying at high temperature, would provide insight into the dominant polymerization initiation mechanism. Now say that 5 times fast. Finally, it would be interesting to determine which types of oils are most likely to bond with the iron surface, and which are most likely to initiate polymerization. This may have more to do with the impurities in the oil rather than the oil itself. Regardless, this simple model has demonstrated a potential descriptor for the unique properties of cast iron cookware. Thank you for watching.